Hi, welcome back we're again talking about simplification. Last time we talked about simplification to go from a complex system of forces to an equivalent system with one force, one vector. We can do better than that. And for coplanar systems, or for any system where you have the forces perpendicular to the moments, we can actually go from a system, a very complex system, to the system of one force, one vector, and then we can reduce that to just one force. So let's look at how we do that, and I'll just do it kind of conceptually, and then I'm going to give you an example problem that will really help you to understand the concept. So here we have a beam, and supported by a hinge and a roller, and it has all these forces, moments, something's going on here, and who knows what, and we're going to basically simplify that system to be an equivalent, I'll put in quotes, equivalent system, equivalent only from the sense of the external support reactions who can't tell the difference between the complicated system and the simplified system. And we're going to reduce that to one vector and one moment. And that's what we did last time. And we actually went through an example and showed that. But we can actually do one better, which is we can take this moment-force combination and we can simplify it to one force, but applied strategically so that the force times the distance equals that moment at that location. So let's see if I can what we'll do is we're going to do this, an example, and I think by the example you'll understand what I mean here, but we will find this value D. This force is the same as that force, but we're going to apply it strategically at a point such that the moment resulting from this force is equal to that moment that we evaluated first. Remember, we evaluated by adding up all the moments. All right, so that's what we're going to do. Let me put it over here. So in this case, we're going to have a very simple beam. It is 6 meters long, and it's supported by a hinge over here, a roller over here. And that's very typical. Hinge, roller, we'll talk about later why. And I'm going to have a 500 Newton vector hitting right here, 500 newtons, and its slope is 3, and I didn't write it very well, 3, 4, 5. 3 across, 4 up, 5 along the hypotenuse, and that is 2 meters from the end. And then if we go over another 2 meters, we have another force, and this force is coming from the other direction. And this one is also 3, 4, 5, but this one has 3, 4, 5. In other words, 3 vertical, 4 horizontal, 5, also 500 newtons. And then we have another 2 meters on the other end. Okay, this is the system. So it's not that complicated. Oh, there is one moment. There's a couple moments over here, which is 600 Newton meters. All right, so let's get our simplified system. We can just add up all of our x vectors. So we have the sum of the forces in the x direction equals, in this case we have 3 over 5 times 500, which will be 300 newtons positive. Here we have 4 over 5 times 500, which would be 400 negative, equal negative 100 newtons. That's my f of x. And my f of y, or my sum, actually what I should have written here, I'm sorry, is my f r of x. In other words, the magnitude of my resultant vector in the x direction and the magnitude of my resultant vector in the y direction. And I'm going to sum those up, and they'll be equal to the sum of the y components. So we have negative 400 newtons, because 4 over 5 times 500 is negative 400. Here we have 3 over 5 times 500, so it's negative 300. Actually, this is just like our other problem from last time. We have negative 700 newtons. That is my y component of my resultant vector. And lastly, we're going to have a 600 Newton meters, but we also need to consider the moments, and we're going to evaluate all this for a point right here. We're going to call that point O. You'll notice that all the horizontal components, their line of action will go right through O. So they have zero contribution to the moments. But we need to consider the vertical forces. So let's do that now. So I'm going to write here M R by O equals the sum of the sum of MO, the sum of the moments resulting from the forces plus the sum of the moments from the couples. And I'm not going to write, let me erase that because we're going to run out of space if I try to do that. But keep that in mind. So what do we have? We have, again, we're right here, and the positive component will be 4 over 5 times 500 downward. Put it in here. That's 400 down, and this one will have basically 300 down. 300. This one's 400, obviously newtons. And they both, if you think about the moment here, they're both going to cause a clockwise rotation, or a negative moment, okay? So I'm going to have a negative 400 newtons times this length, 2 meters. And then I have 300, negative 300 newtons times, now we have 2 plus 2, 4 meters to get to that point O. 4 meters, and then we have 600 Newton meters in the clockwise direction. So that's a negative value. So we have 3 negative values here. Negative 600 Newton meters. So the result will be, that's 400 times 2, 800. 400 times 3, 300 times 4 is 1200, so that's 2,600. Negative 2,600 Newton meters. So let's actually, I'm going to enter this into our chart here, and it's a negative value. So I'm going to fix this, because this one, I drew this as a positive value, right? Counterclockwise. So in our simplified system, we have a negative moment. Negative moment meaning clockwise of 2,600 Newton meters. And then we have a force vector which goes 700 down and 100 in this direction. And I'll just write it as if it were actually, I'll just write its components rather than writing its, the individual, the one vector. So we have 100 in that direction, and we have 700 in this direction. Again, these are newtons. So how do we find a vector, or where do we want to put this vector? Actually, let me start this at this point. Again, it's at point O. This vector, the 100, will have no contribution because the moment arm at that location is always, even if we move this vector in this direction, it's always going to have a 0 component. But we want to move this over somewhere, and I'll do it in red, some distance d, and I'll actually, oh, we did it here, d, here's my d, and we're going to have, again, 700 in this direction, and 100 in this direction, and we want the moment caused by that 700 newtons to be equal to our negative 2,600 Newton meter rotation. And as I was saying, if we move this like in this direction, that 100 newtons is not going to have any contribution to the moment arm at that location. So the trick here is to find that value of D. And so this is not actually that hard because we know that the moment equals the force times the magnitude of the moment equals the force times the distance. So the moment we're looking at is negative 2600. Newton meters. We'll say that's equal to this force, 700. And I'll put negative 700 newtons times D. And so we can find D as 2600 divided by 700. So D equals 2600 Newton meters divided by 700 newtons. And it's going to be equal to, I don't have I do have an answer. The answer is 3.71 meters. So that's how we find our simplified system. Our simplified system has a single vector. We're showing its two components, 700 and 100. And it's a distance of 3.71 meters from the left-hand side from our original point O location. So this shows you an example of how we've simplified a system. First, we have our complicated system. We went to a simple system with one force and one moment. And then we finally ended up with only one moment. And you can only do this in systems where the moment vector is going to be perpendicular from all of the force vectors. And that's the coplanar system, which we've talked about several times before. So that's all I want to talk about now. The next topic will be distributed loads. And I will see you in class, and please send me your questions on any of this material.